All right. So we were talking about congruence, modulo, and ideal, and we want to move on and define quotient ring. But we had quite a lot of definitions last time, so I think I'll review some of it to begin with. And one good way to review them would be to maybe indicate some of the proofs of these little things that we left out as exercises. So let's see where we were. Here's the setup. You have a ring R and a two-sided ideal I. We just say ideal, meaning two-sided ideal. Given two elements A and B in the ring R, you say that A is congruent to B mod I if the difference A minus B is in I. Same as saying B minus A is in I, because if something is in the ideal, its negative is also in the ideal. We verified that this is an equivalence relation on the ring R. Because it's equivalence relation, it breaks up the ring R into equivalence classes. These equivalence classes are called congruence classes, also called cosets. So the coset of A, or the congruence class of A, means the equivalence class of A. Equivalence class of A means all the elements in the ring that are related to A via this relation. And that set happens to be the set of all elements of the form A plus X, where X varies over the ideal I. So a good notation for this set is A plus I. We denote this coset of A by A plus I to indicate that it consists of all these guys. Okay. And then R mod I denoted the set of all equivalence classes, modulo I, meaning the set of all these sets. The set of all such sets. And then we had this little lemma, a bunch of equivalences that tell you when something belongs to a congruence class. Let R be a ring and I be an ideal, same setup. Given B and C in the ring, the following are equivalent. B minus C is in the ideal, which is same as saying that B and C are congruent modulo I. That's equivalent to saying that the class of B is the same as the class of C. And that's equivalent to saying that B and C belong to the same congruence class modulo I. Okay. So maybe I'll indicate a little bit of the proof. So let's see. In fact, even before that, let's indicate a little bit of the proof of this exercise. Let's call it exercise 1. It says that the congruence class of A, remember by definition that means all the B's that are related to A. That happens to be this set. So proof of, let's verify this equality here. Exercise 1. Let's verify at least a little bit. So let A in A, R, and let capital A be the congruence class of little a. I want to show that capital A is same as this set A plus I. So take some B in capital A. What does that mean? That means that B is congruent to A mod I. So this difference is in I. Let's call this difference X. Now you note B is now A plus X, where X came from I. So it does look like A plus an element of I. So it does belong to the set A plus I. What did we just argue? We argued that anything in the congruence class, capital A, is in the set A plus I. So A is a subset of little a plus I. Similarly, verify the other inclusion. It's equally easy. Okay, so we at least verified one inclusion. Okay. Now let's verify a little bit of this lemma that I was talking about. 3 equivalent statements. Let's check one implies true. Proof of lemma. Let's do one implies 2. How about that? So what am I given? I'm given this ring R, this ideal I, and I have two elements B and C in R, and I'm told that B minus C is in I. So assume 1, and that is B minus C. Oops. Is in I. Now you take, what do I need to show? I want to show 2. So I need to show that B plus I is C plus I. So I'm going to take something from C plus I, and I'm going to show that it's in B plus I. And the other inclusion will be similar. So take some element in C plus I, call it A. Then what does that mean? That means A is in the congruence class of C. We just checked that C plus I is the congruence class of C. That was exercise 1, remember? So A is in C plus I. So A is congruent to C, which means A minus C is in I. Now B minus C is in I, A minus C is in I is an ideal. So A minus C minus B minus C, that's also in I. And that just happens to be A minus B, right? So A minus B is in I, so A is in B plus I. What did we argue in these two lines? We argued that if some element is in C plus I, then that element is also in B plus I. So C plus I is a subset of B plus I. Now notice that this just used the fact that B minus C was in I. But if B minus C is in I, note C minus B, which is the negative of B minus C, is also in I, because I is a subring after all. So you can do the same argument, I mean this argument, with the role of B and C interchanged. Take something in B minus I and show that it's in C minus I. So let's put it this way. Since this is so, interchanging the role of B and C in the above argument shows C plus I, B plus I is a subset of C plus I. So B plus I and C plus I are subsets of each other, so they are equal. So 1 implies 2. And the other implications, 2 implies 3 and 3 implies 1, are actually even easier. And once you have that, part B is absolutely immediate. Part B says that if you have a congruence class, call it capital B, meaning a set that looks like something plus I, then if little b is an element of capital B, then capital B happens to be the congruence class of little b. And these two statements are equivalent. So little b belonging to capital B is equivalent to saying that capital B is the congruence class of little b. Okay. That's quite immediate from part A as well.